Welcome to Sarfatti Science Seminar's Cortona 2023 event. It's May 26th, and today's speakers are Dr. Jack Sarfatti on the Advances in UFO Metric Engineering Physics Part 2, and Dr. Gianluca Perniciano on reduction energy in the warp region in Alcubierre Warp Drives. I'm your moderator, Tim Ventura, and we'll begin with the discussion of Advances in UFO Metric Engineering Physics Part 2 by Jack Sarfatti.
Okay, ladies and gentlemen, this is part 2 of my Cortona lectures, and this is going to be basically the real nitty-gritty, hardcore mathematics. Most of you who are not familiar with at least calculus and have taken some physics courses will probably not understand much of what I'm saying, but of course you're welcome to try. So this is really directed not toward the public, but basically toward my peers, people with at least bachelor's degrees in mathematics and physics, and preferably with advanced degrees. And of course, I'm directing this to the intelligence agencies and the militaries that are tasked with trying to understand this military threat, which is very serious in my judgment. So this is Metric Engineering Physics from Cortona, Tuscany. Thanks to Gaetano Battaglini for extending his hospitality to make these meetings and workshops possible. And of course, I'm Jack Sarfatti, and this is a basic concept, a basic idea in Einstein's theory of relativity, both the special theory from 1905 and the general theory from about 1915, about 10 years later. Now, this only really works in vacuum. It doesn't work in matter. The reason you need vacuum is that the vacuum is not dispersive. What does that mean? That means that the speed of light in vacuum does not depend on its frequency. Well, that's only true for low frequencies, but the frequencies that we do astronomy and most of our science, and we're talking about microwaves, infrared, the visible, of course, the visible spectrum, X-rays, gamma rays, things like that. We could pretty much ignore any dependence of the vacuum speed of light on the frequency of the light. And if that were not the case, if the vacuum had dispersion, Einstein's theories of relativity, as currently formulated, would not work. Now, this does not seem to be generally recognized, even among some of the experts in relativity. Nobody really talks about it. I've been looking in the literature, and nobody talks about it. At least I can't find anything. Now, if any of you can find some relevant papers on this, I'd be glad to see them. But you see, this is the key problem in terms of understanding the UFOs, because in the metamaterials, which are the fuselages of these things, there's a lot of dispersion. And what we're interested in is how to apply relativity theory inside matter. And that is pretty much unexplored. If you actually look in the literature, what they do, they talk about the stress energy tensors inside matter, but they never Fourier analyze them. They're only talking about what's called equations of state, the stress energy tensors, as functions of space-time. You seldom see the power spectrum, the Fourier analysis, or even what's called the wavelet analysis that depends on scale. You don't really see that. And of course, that aspect is essential to really cracking cracking the code, reverse engineering these flying saucers, which, by the way, I know our military has them. The U.S. military has more than one, and I kind of know exactly where one of them is, but I'm not I'm not able to tell you guys, but I do know pretty much. I say I know with about 95% confidence level that I know where one is. A Roswell type craft, the kind that Rick Doty and Colonel Phil Corso talk about. So we have this light cone. Let's get back to the physics. So the light cone, you see, the vertical line is called the time axis. And the horizontal plane is that's three-dimensional space. This is, of course, we cannot in our minds, and we can't draw four-dimensional objects. So we've removed one of the space dimensions. So a three-dimensional space looks like a two-dimensional plane. And what we're assuming here, again, is vacuum, that the vacuum speed of light does not depend upon the color of the light or the frequency of the light or the energy of the photon. The energy of the photon is Planck's constant times the frequency of the light. That was Max Planck, 1900. And of course, Einstein in 1905 actually got his Nobel Prize for the photoelectric effect, in which he applies the Planck relation that the energy of a particle of light is equal to the Planck's universal constant times the frequency of the light. And now we're also making an assumption of causality. We're assuming that signals only propagate from the past to the present. These are called retarded light signals, or also ordinary notions of causality, past cause, present effect. Yakia Aharonov, in his quantum theory, he says these are history effects. The quantum waves associated with this are called history waves. They propagate from past to present. Now, it turns out that this is not going to be good enough. This is a classical approximation, but when we come to quantum entanglement, the so-called EPR, Einstein, Podolsky, Rosen, with Lenny Suskind's ER equals EPR, it turns out then, when we talk about the spooky telepathic effects of quantum mechanics that David Kaiser mentions in his book, How the Hippies Say Physics, then we're actually going to need messages back from the future, what are called advanced destiny signals by Yakia Aharonov. But right now we're going to ignore quantum effects. We're not going to talk about the advanced destiny back from the future influences. We're only talking about classical vacuum electromagnetic signals that they move in the past light cone and to the observer here. You see the observer there. Now, every observer, we all have our local light cones, okay? And the big thing about the light cone is that it's an objective observable. That is, if we do what's called a inertial frame transformation, the light cone doesn't change. The light cone is like a fixed beacon when we do what are called inertial frame transformations. I'm going to have to explain that in more detail. It's also called Lorentz transformations. It is the basic feature of Einstein's special theory of relativity that the vacuum coordinates, called the coordinate speed of light, does not change when Alice and Bob are two inertial observers. That is, they're moving without rotating, without accelerating. They're weightless. There are no g-forces. They're moving in space, freely moving in space. And when they measure, say, the vacuum speed of light, they get exactly the same number. But now it turns out this is not really true when they're accelerating or rotating. And that's a big thing. But we'll come back to that as I proceed further. Okay, Einstein's theory of relativity, and I really mean the general theory of relativity of the gravitational field, because special relativity does not explain gravity at all. Einstein's general theory of relativity explains all UFO phenomena. Now, before we proceed further, I have to explain to you what I mean by explain. David Deutsch, a very smart guy from Oxford University, in one of his recent books, says the main function of theoretical physics is to provide explanations, because it's only through explanations, which are stories, narratives, like with the cavemen sitting around the campfire, or Boy Scouts, Cub Scouts, listening to ghost stories late at night. But we're social animals, and we live by our stories. If think of all the time you spend watching science fiction or reading fiction books, things like that. So my objective here is to give you a story that you can kind of understand, a narrative. A narrative that puts all these puzzling phenomena in a kind of coherent picture. It doesn't mean, as a theoretical physicist, that once I explain what the laws of physics are that account for these weird phenomena, doesn't mean that I can immediately go into a laboratory and build one. I mean, that's stupid. When I hear these naive engineer types, they say, oh, well, show me an experiment. I mean, most of these experiments take, because first of all, millions of dollars, hundreds of millions of dollars. And it's kind of like asking Einstein in 1905, when he gets E equals MC squared, and after Madame Curie discovers radioactivity. So, maybe around World War I, when Niels Bohr kind of explains the nucleus of the atom, and people are beginning to realize about nuclear physics. And it's like asking Einstein to go down and design a nuclear reactor, or worse yet, design an atomic bomb. Once people realized fission, that was already Lisa Meitner in the mid-30s, I think around 1936. Everybody realized you could make an atom bomb, because the physics of it is pretty simple. The narrative, the explanation is pretty simple. But to translate that understanding, that explanation, into operational technology, that's the difficult task. And that's, it's like, once you may know the principles of aerodynamics, but you can't go out right away and make an F-35 without a lot of effort, a lot of money, a lot of investment, a lot of brain power. So the same thing here. When I say I'm explaining UFOs, doesn't mean I can go and tell you how to build one right away, how to reverse engineer it. And also we have all these, if you listen to John Warner, in his first talk of this series, where he says, and other people have said, that most of the attempts at reverse engineering have cost billions, maybe even trillions of dollars, black budgets over 70 years, and they haven't been able to do it. So, because why haven't they been able to do it? Because they don't understand the basic explanation I'm about to give you. You see, in order to reverse engineer these things, you have to first have the kind of conceptual understanding that Jack Sarfatti is providing all of you people whose minds are not closed to various, mental illnesses, to accept, or at least consider in a rational way, what I'm trying to explain to you. Okay, so let's proceed. What are the basic ideas of Einstein's two theories of relativity, both special and general? Here's the classic, what's called the Gedanken experiment. We theoretical physicists, we're lazy dogs. We basically are in our heads. We're kind of like mathematicians, but we're more practical than mathematicians. Alice and Bob move relative to each other in any possible way. That is, they're moving slower than the speed of light. And also we have to picture now, Alice and Bob are out in space now. Okay, they're not, well, they could be standing on the Earth, but then they're what's called non-inertial observers. But Alice and Bob, let's imagine them like in space suits, and they're out in space in free float. and moving relative to each other, but also they have backpacks, so they have rocket that they can accelerate. They can fire their little backpack rockets and accelerate, but they can move in any possible way relative to each other. And then they're looking at something. They're looking at, oh, they see a UFO, they see a flying saucer out there, and they're observing the signals, the light signals, or they could be microwave signals or radar signals, radio signals, any kind of electromagnetic signal that's coming from these events. And they're both looking at the same thing that's happening out there in space, and they're recording. They have sophisticated detectors, and they're recording their data. But they wish to compare their measurements of these same events. Now, the theory of relativity is essentially an algorithm, and which is now implemented in a computer program and a database, into which they enter their raw data as inputs, and lo and behold, the computer does its thing, executes the relativity algorithm using Mathematica or any of those programs, and what happens? They get exactly the same output numbers, called frame invariants, or observables, if you like, objective observables. It is this agreement that proves objective reality independent of our consciousness in classical theoretical physics. And again, I have to emphasize that this was a core belief of Albert Einstein and of all good physicists. It's still the core belief. We're all objective. We don't believe that consciousness creates reality. Some of us believe that, but I don't believe that. I don't believe consciousness creates reality. I believe consciousness is an objective phenomenon as part of physical reality, and that consciousness emerges under certain conditions. But we'll get back. That's another issue. That's called the hard problem that both Maurice Passman and Eric Shemansky yesterday, they gave very good talks about that, which you can see on the Tim Ventura's channel. But we'll get back to that later. So let's continue. Now, the same objectivity, the same is really true in quantum mechanics. Using David Bohm's 1952 pilot wave interpretation that he did with Einstein at Princeton, as updated in 2015 by Roderick Sutherland in Sydney, Australia. Sutherland took David Bohm's 1952 theory, which was non-relativistic, and he made it fully relativistic. But in order to do so, he had to introduce Yaki Aharonov's future, back from the future destiny effects, which comes in what Aharonov calls weak measurements, and we'll get into that later as well. And it turns out that in order to explain quantum entanglement, which was called non-local entanglement, like if you have two particles that are far apart from each other in space, nevertheless, in a certain sense, both particles know what the other particle is doing, even though no classical light signal limited to the speed of light can connect them when certain things happen to both of them. So, and Einstein called that spooky telepathic psychokinetic action at a distance. But now what Sutherland did was to show that you can eliminate this spooky fast than light and sort of be consistent with Einstein's special relativity. But in order to do so, you have to give up the idea that signals can only propagate from the past to the present. You have to allow them to propagate back from the future to the present as well. Both of these things happen together. So what does that mean? That also means what we call the block universe. It means that everywhere in space and time is objectively existing. It refutes the idea that the future is not really determined yet, that things kind of, like it kind of comes into being. No, that doesn't work. And we now have evidence that that doesn't work. And it's called the block universe, which was Einstein's original picture of the block universe. So this is an important thing. Also, by the way, I have to digress a little bit. Gaetano gave me this book, an interesting book. I'm gonna have to buy it, from Cambridge, called Conversations on Quantum Gravity, edited by this guy Jay Armas, and all these interesting conversations, like with Lenny Susskind and Gerard de Hooft, that I'm reading. It's very good, and they're talking about their views of physics. And I realized, let's take de Hooft. Gerard de Hooft. Let me digress. De Hooft, a Nobel Prize. I mean, very smart guy. I mean, he's a brilliant. He's in Holland, and he got his Nobel Prize for doing these very complicated renormalization calculations, showing that that the standard model, weak strong interactions, they're renormalizable, all this stuff, brilliant mathematics. But I understand he's very limited. He does not accept back from the future. He doesn't, it's a philosophical, metaphysical, he's got a block in his mind, as far as I'm concerned, that he says signals can only go from, the past to the present. In other words, his notion of causality is rigidly fixed, and I believe that's his fatal mistake in terms of solving the big problem he's trying to work on. Now, I could be wrong, he could be right. But I realize he doesn't, he says, I reject, he says, de Hooft says, I reject closed time-like curves. And without that, he's dead in the water in terms of quantum gravity and even entanglement. And so I mentioned that passing, and also Lenny Susskind has some good things to say in there. And I haven't really read a lot of good conversations in here. I recommend the book. I'm going to get it. I'm going to read it when I get back, when I have time. And okay, let's continue. And I'll stop here for the next slide. Okay, more on now Einstein's explanation or narrative about the gravity field. We're talking about general relativity, well, 1915, 1916. Isaac Newton, in the 17th century, thought that three-dimensional space and one-dimensional time were independent from each other, together forming an absolutely rigid stage on which events played out in the cosmic theater directed by God. And you even see this, the Shakespeare plays, the world's a stage, and so on and so forth. I guess that's in Tempest, Prospero. Einstein, 1915, 1916, after 10 years of struggle to get beyond his 1905 special relativity that explained electromagnetism but could not explain gravity, Einstein realized that the stress energy density of matter distorted, warped his unified, rigid, four-dimensional space-time continuum of his special theory of relativity, and that this warping or curving was real, what we now call second order, it's called tidal gravity, as opposed to the artificial first order gravity that we feel as weight or G-force, but only when there are electrical reaction forces that prevent us from freely floating or freely falling in space. This equivalence principle was Einstein's happiest thought when he read that a painter falling off his ladder said he felt weightless. Einstein's general relativity is about geodesics. Remember now, we have this picture of a four-dimensional space-time and the motion of particles. Think of tiny little, like point particles as a first approximation. They move along curves, one-dimensional curves called world lines in this four-dimensional space-time, which obeys a Pythagorean theorem of a certain kind. You from elementary geometry, trigonometry, you learned the Pythagorean theorem for right triangles, that the square, the hypotenuse, is the sum of the squares of the size of the triangle, the legs of the triangle. You all remember, maybe some of you, Pirates of Penzance. I am the very model of a modern major general. I've information, vegetable, animal, a mineral. I quote the kings of England and battles historical, and I answer hot acrostics. I have a pretty taste for paradox. I'm teaming with a lot of news about the square of the hypotenuse. So I'm teaming with a lot of news about the square of the hypotenuse. That's basically, that's in a nutshell, that's Einstein's theory of both special relativity in a certain sense. It's called, we'll see that in a little while. We get to the mathematics of that. So let's go on. Now, geodesics, this is the most important thing. The geodesics are the trajectories on which the flying saucer moves when it's in warp drive. A geodesic is a straight line in a curved geometry. That's a little counterintuitive, isn't it? It's a straight line. By the way, this slide is not from me. This slide is from David Chester, and I may have modified it a bit to make it a little more accurate. So geodesic is a straight line in a curved geometry. In other words, it's as straight as it can be. It parallel transports itself, what's called the tangent vector. It's as straight as it can be locally, but the space itself is curved. So to an observer looking at it from a distance, it's going to look like a curve, like the space station in free orbit. Looks like a circle or an ellipse, but it's really what's called on a geodesic, a time-like geodesic. So a geodesic is a straight line on a curved geometry, which means it has no turn. Such a line may not look straight, but it is. That's David Chester's words. Objects in the universe are embedded in space-time, which has a curved geometry, depending on the masses or the source mass. But now the masses, there are actually three kinds of mass. David here is talking about what's called active source mass. That is the mass that actually creates the curvature in space-time, according to Einstein's general relativity gravitational field equation. So that's the active source mass. But there also is what is called the passive gravitational mass, which is how the object responds to an external gravitational field. So that's called passive gravitational mass. And then there's still a third thing called the inertial mass, which is what high energy particle physicists, they mainly think of inertial mass. And in particular, something called the rest mass. And the rest mass is the resistance when you use, let's say, an electrical force. The mass has to have an electric charge, and use an electric field to actually push the particle off its natural time-like weightless geodesic. We're assuming now the particle's out in free space, because remember, relativity is really only formulated for what are called test particles in free space and in vacuum. And the idea of a test particle is that we can ignore its active mass. There's some views like the Earth, like for example, Jack Sarfatti would be a test particle relative to the Earth, unless we had really accurate instruments, and they do exist now. We could ignore the gravitational field my active mass creates, and basically make an approximation that the only thing that matters is the Earth's mass. So that's called the test particle approximation. So let me repeat, objects in the universe are embedded in space-time, which has a curved geometry depending on the masses or the active source masses within it. We're not pushed by anything, but push means an electrical force. We're not pushed by an electrical force. Objects move along time-like geodesics. They're the straight lines of that curved space-time geometry. But these time-like geodesics, their velocity is less than the velocity of light. And in terms of the light cone pictures that we can see a lot of, the time-like world lines, the geodesic world lines, are inside the light cones, both the past and the future light cones. So that means that we're moving subliminally, and that's when you hear that nothing can move faster than the speed of light, that's what they're talking about. That means locally that you're on a time-like world line. It doesn't even have to be a geodesic. You can be accelerating. It could be off geodesic, but you're always inside your local light cone. And it would take an infinite amount of energy to actually reach your light cone, which is where the light rays are. That's where the speed of light goes. And in three-dimensional space, you could think of the light cone as really a spherical wavefront coming from a point source. That's the three-dimensional picture. In four dimensions, you think of a cone, but in three dimensions, you think of a spherical wave, expanding spherical wave. It's expanding into the future. That's a retarded history wave from a point source. Let's see Huygens, it's called Huygens principles, another thing to look up, Huygens principle in optics, wave optics. So this means geodesics are the trajectories of freely falling objects. The Earth, for instance, curves the space-time around it, and objects simply follow that curvature, which we call gravitation. Okay, so that's the basic picture. It's very different from Newtonian picture. In Einstein's theory, there's no such thing as a real gravitational force. The whole idea of gravitation, in the case of massive particles with rest mass, and also with passive gravitational mass, because actually the inertial mass is equal to the passive gravity mass. That's called the weak equivalence principle, or WEP. Let's continue. Examples of geodesics. The trajectory of a baseball thrown on the moon where there's no air friction. And to a pretty good approximation, well, no, actually, I guess air friction can be important in baseball and in football, all those things. They have, curved ball, yeah. So, yeah, what he says is good. The trajectory of a baseball thrown on the moon where there's no air friction is a geodesic path. The motions of all objects in space, such as the orbits of moons, planets, and asteroids, to the extent that they're moving through a vacuum, which is pretty good approximation. There are things like the solar wind, there's dust, stuff like that, but it's pretty low density. So it's a pretty good approximation. The orbit of space stations, space debris, satellites, assuming their rocket engines are off. As soon as they fire a rocket engine, you're no longer on a geodesic, and that's why you feel G-force, just like when you step into the Ferrari and step on the gas, and when you take off in an S3 on an aircraft carrier, you feel that when the catapult launches you, as I have done. Remember, a geodesic is a curve that locally has no turns in it, but globally looks curvy. So yeah, this is important that David Chester is emphasizing this, because we have to get this distinction. It's going to be very important later, especially for UFOs. To get this distinction between a local point of view in a tiny little region and a global, the big global kind of topological point of view. So remember, a geodesic is a curve that locally has no turns on it, but globally looks curvy. Now, if you're beginning to feel like Alice in Wonderland, that's good, because that's the general relativity is like you're like Alice in Wonderland. And if you're a male, then you could be a transgender Alice in Wonderland. All right. That's if you're a woke person. All right. So this is oh, I see now. This is a quote. This is a quote from that guy Thor. I guess I thought it was David Chester, but I forget where I got it from. This is a guy Thor. I gotta mention him. He's a mysterious character. He was. He's some kind of, I guess he has a master's degree in astronomy, astrophysics, and he's a smart guy, and he did like he did like a Sherlock Holmes, like what Paul Hill did in the 1950s, not knowing Paul Hill was an engineer, aeronautical engineer. He did not understand Einstein's general relativity. He didn't have the language for it that we have. And he kind of deduced, Paul Hill sort of, from the reports that he had back, 70 years ago or so, he called it an acceleration field. But what he was really talking about was the gravitational field, but he didn't quite realize he was just talking about Einstein's gravity field. He deduced a lot of the ideas of warp drive. Just from just from being like a Sherlock Holmes forensic analysis of the observations and using his very limited understanding of Einstein's relativity theory. In fact, he didn't have any understanding. He just was using Newton's ideas. But he came up with a primitive idea of warp drive. And this guy, Thor, looking at the recent data and knowing some general relativity, he's more sophisticated than Paul Hill, but basically came up with the more sophisticated explanation that all these things have to be warp drive. That explains the high accelerations. So what Thor did do, independently of Jack Sarfatti, was to come up with the same explanation that the only way, say, to understand Luis Elizondo's 5 observables is that it's warp drive. Okay. What Thor could not explain was how you could achieve warp drive without huge amounts of energy. See, that's what I did back in 2011 when General Pete Worden, then retired Brigadier General from the Space Command, took over NASA Ames, and Creon Levitt, who's you see him on this set in this workshop. Creon Levitt was his right-hand man, and because of that, I got invited to this, which I helped actually set up this 100-year Starship, joint project of DARPA and NASA, and Larry Lemke was there too. And I presented back in 2011 the idea. I said there's such a thing as low-power warp drive. It's because we have to use metamaterial resonances, and those resonances amplify the coupling of electromagnetism to the gravitational field, and that's why we don't need a lot of energy. But the resonance has to be very strong. Doesn't mean I know how to make a material that'll do that. But well, from the observations, that's the only explanation. That there is no other explanation other than to throw up your hands. It's new physics. We don't know the physics. You have to wait 1 million years for the physics. No, we know the physics already. Okay, so no cheap solutions, but we how to engineer it, how to make it into operational technology. That Jack Sarfatti doesn't know how to do that yet. All right, so Thor came out with this, but then something happened. Something spooked Thor, and now nobody knows what happened to him. Maybe he's dead. Maybe they assassinated him. We don't know. He disappeared. Fortunately, Tim Ventura has his website, so we haven't lost his information. But basically, what his investigation corroborates my general narrative, but it doesn't explain the dynamics, how to solve the energy problem. That's what Thor reproduces my general explanation, but he doesn't have my particular dynamical explanation of how the metamaterials fit in. And that's another thing, by the way. You hear Luis Elizondo and Hal Puthoff and their talks, they mention metamaterials, but they never explain the physics. They never explain why are metamaterials important for the UFOs? They never explain it. In fact, the way Eric Davis and Hal Puthoff use metamaterials, it's the same thing like Lazar talks about element 115 at area 51. I mean, there's no physics. They don't explain what is there about metamaterials that explains the warp drive. They have no idea. I tried to explain it to Hal, but he didn't quite get it. We didn't, All right, so let's continue. So I'll stop this slide here. And okay. Now I forgot to emphasize something in the last slide. Remember I said there are 3 kinds of mass. There's the active source mass, which creates the curvature in space-time, which bends the space-time, active source mass. There's also the passive gravitational mass, which is how it's got to be a test particle, how a test particle responds to the curvature field created by some other active source mass, okay? And then there's the third mass, which is called the inertial mass. Okay. Now, the weak equivalence principle of actually goes back to Galileo. It was Galileo, I guess, was 16th century. Is it 1500s? Or I forget. Or is it 1600s? Galileo's equivalence principle, the Leaning Tower of Pisa, that he dropped the different objects, they all universally accelerated down. They arrived at the same time. Also, he did the inclined plane sort of thing. And you have to correct, of course, for friction. But the idea is that the weak, the passive gravity mass is exactly the same as the inertial mass, okay? That's called the weak equivalence principle. And it's because of that, when you actually plug in the equations, even in Newtonian gravity theory, this is both true in both Newtonian gravity theory and also carries over into Einstein's general relativity theory, because, and we'll see that in the math later, because the inertial mass is the same as the passive gravity mass, what happens is that all, and again, only test particles, all test particles fall the same way, have the same acceleration when you actually do experiments. Now, wait a minute, now you see there's an issue here. Test particles means that you can ignore their active source mass. So the whole idea of a test particle approximation is that we don't have to worry about the active source mass of the test particle, because if we did see a UFO, okay, now a flying saucer is not a test particle. Well, okay, a flying saucer, it can, if it wants to behave like a test particle, it could switch off, so to speak. It could switch off its effective active source mass and only have passive gravity mass and its inertial mass. And in that case, it'll be just like any ordinary object in the Earth's gravitational field. It can masquerade itself as a test particle, but when it switches on its warp drive generator, it develops a huge, an effectively huge active source mass. But now notice right away, we have a dilemma coming up here. What people accept, even what the people in general relativity, they talk about the equivalence principle, but they don't emphasize that the equivalence principle breaks down if it's not a test mass. But a test mass, right away, a test mass, the active source mass is not the same as the inertial mass and the passive gravity mass. Now, there are some experiments, allegedly, there's the Cavendish experiment, and they claim, and I think this is a mistaken claim because they haven't really understood what the Cavendish experiment, people will tell you that the Cavendish experiment shows that the active mass is the same as the inertial mass and the weak mass. And actually, that's not true. I don't think that's true, because they've neglected the fact that the electrical reaction forces in the torsion wire will compensate for any change, and it's not going to affect the basic. What the Cavendish experiment gives you is a value for Newton's big G, his gravitational constant. And there's enough play in the electrical reaction forces in the torsion wire that you always get the same, basically the same number for a gravitational constant, even when the active source masses are different from the passive mass. That's what I claim, and we can argue that, but it's a it's a technical point, but it's very important in terms of the flying saucers, metric engineering. So the point is this: what happens when the flying saucer switches on the Sarfatti field resonance, and it amplifies? What happens? It amplifies the coupling of the electromagnetic field that's inside the metamaterial fuselage. It amplifies that coupling of that electromagnetic. It's like the rocket fuel, except it's not a rocket. The fuel is the applied electromagnetic field inside the metamaterial. You turn the switch, you switch it on, and you get into a resonance state. And what happens is suddenly the UFO has has a very large active mass. It's able to compete against the Earth's active mass. So what happens in that situation? Now, see, this is now called the two-body problem in general relativity. It's not an easy problem, because when you look at textbooks on general relativity and they show you the orbits of particles, the orbits of the space station, all that stuff, those are all assuming they're test particles that are moving in the time-like geodesics generated by the Earth's mass, or if you want, the orbit of the Earth around the sun. Then the sun is the big thing, and the Earth is itself, like relatively speaking, a test particle relative to the huge mass of the Earth. But what happens if you want to get more accurate? Suppose if we had really accurate measuring instruments and we did Galileo's experiment, dropping a copper sphere and an iron sphere from the Tower of Pisa, and if we really had accurate measurements and we're able to measure really tiny effects, we would see maybe that the source masses of say the iron ball and the copper ball was slightly different, and there'd be very slight differences in the way they fell. But they're so small that we normally, with our current measuring instruments, within the era of our technology, we don't notice these differences. But in fact, there would be a difference. And this is called the two-body problem, of course, the n-body problem. Because in principle, what you have to do, suppose I have a flying saucer, a tic-tac, that's in warp drive, so that it has a significant effective, I call it effective active source mass, that is able to compete and cancel out the effect of the gravitational field of the Earth. That's what warp drive is doing. It's controlling its own time-like geodesic. So what you have there, it's a complicated problem. It's because it's a nonlinear problem. And what you have is you have two sources, each generating a gravitational field, and there's a composite gravitational field. And if there are no electrical forces involved, in the case of the Earth, there are other forces, it's friction and all that stuff, the atmosphere, and but what happens, you have to solve this what's called this two-body problem, and generally the n-body problem, and that both, if they're out in free space, and if you could forget about electromagnetic effects, both the centers of mass of both of these objects will move on their local time-like geodesics of the combined gravitational field. Okay, so now this is very important for understanding the U.S. Navy close encounters with the Tic Tacs, because what Commander Fravor and his the other people in his team, and what Kevin Day, the radar officer, reported, they're seeing the Tic Tac is able to control the gravitational field inside its fuselage, and is able to counteract the Earth's gravitational field. And that's what we see going on there. So let's get back to this slide now. Apparent high G-force accelerations, easily understood in terms of Einstein's general relativity warp drive. The flying saucers, they call them I like to call them flying saucers. Okay, or Tic-Tac, even Tic Tacs. UAPs, that's Kirkpatrick and all these military guys. They're trying to like sort of hide what's really going on. I guess they're trying to make it more acceptable to the senators and to the to the people who don't really understand this stuff, and trying to sell them that it's real and maybe get some money from them. But whatever. I'm calling flying saucers, with little green men with the with the ETs and Mars attacks, all that stuff. So the flying saucers demonstrate linear accelerations within 1 second to speeds higher than ordinary aircraft. I didn't write this. I don't know who wrote this. They're also able to maneuver around sharp angles. Yes, they are. John Warner IV, and his first lecture, talked about how stupid it is, when the jet plane, the F-18, is trying to catch a flying saucer, and the flying saucer makes a quick quick right angle turn, and it'll take 50 miles for the F-18 to catch up with it using conventional propulsion. So I mean, yeah, there's no contest. There's no contest. If Vladimir Putin's Air Force get this technology before the US Air Force, it's all over for the US Air Force. It's all over. They can't, there's no defense against a Russian Air Force equipped with the technology I'm telling you about, okay? So that's why this is a very important problem, okay? And which is why I'm claiming the US intelligence and military is failing, really failing in doing their job here. It's gonna be like another 9/11 on steroids if they don't wise up pretty quick to what I'm trying to tell them. All right. Examples. At one point during the 2004 Tic Tac incident, the flying saucer, the Tic Tac, moved on the radar from 80,000 feet to various altitudes, from 28,000 feet to 50 feet above sea level in 0.78 seconds. Okay, this data, you know, you hear different things, but it's roughly so. I mean, the point is, this is, you know, not possible with ordinary technology. A motion in that time frame along, say, a 60,000 foot distance yields accelerations above 12,000 G-forces and speeds above 100,000 miles per hour if we assume half the distance was used to accelerate and the other half to decelerate. I guess this must be Kevin Knuth. This must be Kevin Knuth. And his, you know, what he's saying is absolutely true. You know, but what does it mean? It means it's warp drive. See, with warp drive, that 12,000 G-force is a mirage. It's optical illusion. It's only what's called the kinematic motion because you know, the radars, the sensors of the U.S. Navy pilots, they're receiving electromagnetic signals from the object that's in warp drive going through the warp bubble, but inside the ship it's 0 G because on time like geodesic, because it's controlling its gravitational field. And until you understand that, you can't understand any of this stuff. And sadly enough, a lot of people, they're not able to get what I'm trying to say here. And until you cross that conceptual gap, you're going to be hopelessly confused. Hopelessly confused. And I'm talking about a bunch of engineers. You know, there's anybody you hear they talk about. There's this guy that we had. I'm not going to mention his name. But, you know, he didn't get this, and he's talking about mass reduction. You have to reduce the mass and shield the mass. It's all bull. There's all nonsense. And even Jim has met anytime you hear that they're reducing the mass, turn off. The guy doesn't know what he's talking about. It's totally, you know, the guy is not competent to talk about this subject. All right, so let's go on. Routinely, the flying saucers are measured and observed to suddenly move very quickly, starting at hundreds of G-forces, the extreme case as described above. Okay, this is all true. That's all based on, like, oh yeah, the paper Avi Loeb and Kirkpatrick, the big shot, you know, heading the Pentagon thing. They don't know what they're doing. They're basically repeating this kind of stuff, but they don't mention warp drive. Somehow, to them, to these idiots, I'm sorry, I get angry. These guys, you know, they missed the boat. They should at least mention warp drive. They think somehow warp drive is science fiction. Okay, so why they left it? They're left with scratching their heads, you know, scratching their butts like monkeys. They don't understand. They're not going to explain that. You know, it's not going to help solve the problem. So this is extremely important. It's a political problem too, because I have to tunnel through what I call the stupidity barrier. The stupidity barrier is very high. And this reminds me of Einstein. He says, there are two things that may be infinite, the universe and human stupidity. And he's not sure about the universe. All right, and that's basically, I'm repeating what Einstein said here. So I'll stop here. Okay, I have to say something I forgot to say. I should have emphasized in the last slide when I was talking about how the flying saucer, when it switches on its warp drive generator, the electromagnetic fields inside the metamaterial hull, when it switches on the juice there, it can make the effective active mass negative. remember, you need negative mass, anti-gravity, repulsive, the blue shift, that's where the blue shift that made Travis Taylor sick, maybe, and all these other people got sick. You know, that Stanford professor Gary Nolan is studying their blood that CIA scientist Kit Green allegedly gave him. You know, they all got sick from the anti-gravity negative mass blue shift. And then you'll see yesterday's talk, Larry Lemke, I think he's going to talk again. Larry Lemke, who's retired from NASA, analyzing the Roswell metal foil, thinks that there may be a kind of a weak anti-gravity field emanating from the surface of the Roswell fuselage material that they have information on, intelligence on. I should say there that my late friend Don Rich, who was a Marine, interesting guy. He actually grew up in Idaho, and his father worked with Kenneth Arnold. The Kenneth Arnold, the pilot who first saw the 7 flying saucers back, it was in 1945, I guess 47 or so. Also, back in the 40s, he was a little kid. And his cowboys, you know, they're up in the ranchers up there. And his father was working for, doing work for Kenneth Arnold. And Don, as a little boy, heard firsthand accounts of when Kenneth Arnold got back saying about the flying saucers. And then Don's brother is in the Marines, an officer in the Marines, and Don joins the Marines, he's tank commander, all that stuff. And then he gets out of the Marines, and he's a sculptor. He has a foundry in Oakland. This is back now, I guess, in the 60s, already in the 60s. And the CIA guy, Colonel Harry Wolf, we don't know what his real name is, comes and says, look, you're a good Marine, the CIA needs you. And basically what they have him doing for a couple of years, he's the courier for the retrieved Roswell materials, taking it to taking little pieces of it to different laboratories. I know he went to France, he gave to the French intelligence there, he went to MI6, he even went to Japan, he even went to apparently in China. Or somewhere near, maybe Shanghai or Singapore, I don't know. But he did this for a couple of years. And he actually had in his possession for a while, Army duffel bags at AAF Roswell on it. And he took out this piece of material, exactly the same kind of material that Larry Lemke describes in his talk yesterday. You'll see the talk, if you see the video of the talk. So, and also even with the hieroglyphs on it. Same kind of symbols that Phil Corso reports. So this is all, I got this all independently, you know, and sadly enough, Don passed away just about a year ago. Well, a little more than a year ago, February of 2022. So that's another piece of information that I'm throwing in there because Larry Lemke talked about this in detail yesterday, and he may talk today or tomorrow, amplify it a little more. But so with the energy problem, I have to emphasize that the flying saucer is able to make the effective mass negative. Okay, let's go back to, this is our fundamental structure, the light cone. Every point event in space-time, you imagine these light cones are there. And again, this is an invariant structure. If Alice and Bob are two inertial observers moving without any g-forces on them out in space, this is moving along time-like geodesics, and anytime they measure, say, the speed of light in vacuum, they're going to get the same number. And that basically means that these light cones are objective invariant structures, properties of space-time. And again, now, if we only think of signals that move one way in time, what we call, let's say, from the Big Bang, the communists say from near the Big Bang, so they're moving, to Earth right now. Look at this past, the past, what's called the past light cone. In three-dimensional space, that's like a spherical wave that's collapsing and collapses to a point at the detector. That's what that means. So the receiver, anytime, like when Commander Fravor is looking at a UFO with his radar and even with his eyes, he is seeing converging, collapsing spherical wavefronts that go into his detector or his eye right at the observer at this point. That's what he said. He's only getting information from his past light cone. And same for the radar, the USS Princeton. This is all of us. This is, whenever we see anything, we're seeing the past. But the speed of light, of course, is so fast normally, even in atmosphere, that it seems almost instantaneous in terms of our ability to process information, our conscious, experience of time. Everything seems to happen almost instantaneously, but it's not really with modern instruments. When we transmit, what the signals you're getting, I'm transmitting now to you on my future light cone. It's going on my future light cone, but you're receiving it on your past light cone. So you got to now again to try to get this picture in your head. Pretty tricky. And outside the light cone, that's faster than light. That's called the elsewhere. Okay. So I'll stop here. Okay, in the next few slides, I'm going to try to give you, especially for your right brain artistic people, I'm going to try to give you a visual picture, a visual narrative to understand Einstein's relativity, kind of in a very intuitive but very important way. And this is a picture really that was developed by Roger Penrose. Roger Penrose, the guy who works with Stuart Hameroff now on the hard problem, trying to explain consciousness of the microtubules and the gravity collapse and all that stuff. And Roger, he just got a Nobel Prize in physics for his work with Stephen Hawking on black holes. I was at Berkeley College in 1971 with David Bohm, and Roger was there as a young professor. And I was one of 3 or 4, maybe 5 postdocs and grad students that sat in, and when Roger tried to explain twistors, his twistor theory, which I didn't really understand too much of it, but I dutifully went to all his seminars. And any case, but Roger also comes from a very brilliant family of artists, and his if you look at his lectures and his books, he draws beautiful colored kind of crayon pictures that illustrate. In any case, this picture is really from Roger Penrose, how to picture general relativity and curvature in terms of these light cones. And Roger's use of light cones are very similar to Richard Feynman's use of his Feynman diagrams, but Roger is working in space-time, and Richard Feynman is doing a very similar thing in what's called energy momentum space, or Fourier transform space. But what Richard Feynman does in quantum electrodynamics, which is the basis of all modern quantum field theory, everything that 't Hooft and all these guys have done, they're all based on Feynman's intuitive techniques of perturbation theory using Feynman diagrams, very similar dual to what I'm about to show you with Roger Penrose's light cones. So let's proceed. Now, this is from the Stanford University Encyclopedia of Philosophy, which is online. It's a really good resource. I recommend serious students use that resource. And this is the section on light cones and causal structure. Remember, this is what Gerard de Hooft takes this as primary. He doesn't want this is Roger. This is Gerard de Hooft's security blanket. This what I'm about to show you. He clings on to this, makes him feel better. In attempting to diagram relativistic space-times, one of the most important features to capture is the causal structure of the space-time. This structure specifies which events, that is, which points of space and time, can be connected by trajectories that are slower than light, and which events can be connected by trajectories traveling at the speed of light, and which events cannot be connected by anything traveling at or below light speed. Try to know, this is important. This is really important. This is the cornerstone of our temple here. Yeah, we'll get beyond it, but this is, you really have to understand this. If you don't understand this, you can't understand anything about UFOs. Just give up. So go do your homework and on your own steam, read this section, 20 times if you have to until you get it. Events in the first group are said to be time-like related because a physical clock could travel from one event to the other. Events in the second group are light-like related because a light ray can travel from one to the other. Events in the third group are space-like related. Given that it's physically impossible on some standard interpretations of relativity theory for any causal process to exceed the speed of light, these three ways of being connected tell us whether one event is able to influence another event. Okay, again, this is Gerardus de Hooft's. He will not budge on this one. And okay, classically, in terms of our macroscopic experience, this is all true. But remember, there's a fly. There's a fly in Mr. de Hooft, Professor de Hooft's soup. There's a fly. What is that fly that's in Professor de Hooft's soup? The fly is what happens. This only works in vacuum. This only works because the vacuum does not show any dispersion. The vacuum coordinate speed of light does not depend on its frequency from very low, in terms of most of our instruments. It does depend on frequency, very high energy, what's called the ultraviolet limit, especially down by the what's called the Planck scale, where quantum gravity allegedly works. So this is an approximation, and we're lucky. This is contingent because, if you believe Lenny Suskind's string theory, there are 10 to the 500 possible universes, all with different laws of physics. That means there are many universes in which the vacuum may be dispersive. There's no reason in principle why the vacuum can't be dispersive, because we know in quantum electrodynamics that the reason the whole idea of the speed of light in vacuum comes from photons at real photons that are scattering off what are called virtual electron-positron pairs, 0 point fluctuating inside the quantum vacuum. There are other things that contribute, but the main contribution is to the virtual electron-positron pairs. So the reason for that the speed of light is 186,000 miles a second is purely contingent, and maybe there could, in principle, be parts of the universe where that's not true. There are different. The vacuum can be in many different. The vacuum has structure. This neutral plasma, what are called virtual particles in the vacuum, so-called 0 point energy, that Hal Puthoff likes to talk about. So this is a very contingent thing. It only works because the vacuum is not dispersive for at least the regions of electromagnetic spectrum that that our technology uses, and this is a stroke of luck. And the question is, what happens inside matter? And relativity becomes very tricky there. And in fact, if you read some of the early books by the pioneers like Arthur Eddington, his book on the mathematical theory of relativity, and especially this book by Richard Tolman from the 1930s. Eddington's book is like 1924, and Tolman's book is like 1932 or something, lectures at Caltech. And they briefly mentioned that, even in special relativity, the symmetries, these frame transformations inside material, well, first, it's hard to imagine what they even mean, because you can't really, if you're not in vacuum, you can't make these transformations. And basically, you're limited to saying if you really want to do practical things, you really should stay, if it's a solid material like a crystal, just stay in the rest mass, the rest frame, the rest frame of that material. Now that rest frame can be accelerating, which you'll see acceleration effects, or it can be freely floating on a time like geodesic. And basically what both Eddington and especially Tolman say is that you don't gain much physical insight by trying to do the relativity frame transformations when you're talking about condensed matter physics, what's happening inside the matter. Because all that, the only thing that relativity tells you is that if Alice and Bob are outside the crystal, let's say, the metamaterial crystal, if they're outside and they're looking at signals coming from it, they're able to deal with that. But if Alice and Bob are like little Maxwell demons, little tiny observers inside the material, and then you have to worry that these materials are very dispersive, so it's not clear what to do. Now, what in fact we do simply as a crutch, because we don't know what else to do, what we do, let me tell you what we actually do. And there's some good papers about this. There's actually a paper by Matt Visser on the archive. It's called Covariant Electrodynamics Inside Matter. And what we do, we take the formalism of general relativity and special relativity, which is what's called the tensor formalism, which really is only derived in the vacuum, okay? And then we can talk about little particles, microscopic level, little particles moving through the charges, moving through the vacuum. And everything kind of works, it makes sense there because there's really a low density of charges moving through vacuum and electromagnetic field. And we can apply the tensor and spinor. There are also spinors if we're doing quantum mechanics. But spinors are basically square roots of tensors. So we use the mathematics of tensors and spinors in vacuum. And when we have these little charges moving through the vacuum, everything works pretty good. And that's the real domain of validity of both general and special relativity. But then when we get into condensed matter, we have to do all kinds of what's called statistical mechanics and coarse graining and averaging. And we get what are called constituent parameters. Constituent parameters like the dielectric, the electrical permittivity, the magnetic permeability, and there's all kinds of other things. If you apply an electric field in one direction in these anisotropic crystals, you get a magnetic field in the other direction. It's very complicated. It's anisotropic, non-stationary materials, in which the speed, what's called now the phase speed of light in the material depends on frequency. And then you have what's called you have different kinds of speeds of light. Then you have what's called the group speed, and you also have what's called the wavefront speed, the signal speed. It gets pretty complicated. And a guy, Louis Brillouin, figured that out. And the Ray Chow, who's a retired professor at Berkeley, he's published a lot on this stuff, how to do it right. But what we do, we get these what are called the parameters of the material, constituent parameters, electrodynamical parameters, that what are called susceptibility, response functions of the material, and we make tensors. We make tensors. The various properties of the material, what are called the coarse grain macroscopic emergent properties of the material from condensed matter physics, become components of tensor quantities. And we combine these tensor quantities with the applied external electromagnetic fields or whatever any other fields we may have. And so we have a formalism that we use. And basically, it's an argument from continuity that we don't know what else to use, and by continuity, it should work, and it does seem to work pretty well. But what I'm saying, it rests on shaky ground, and even when you look at even Matt Visser's paper on covariant electrodynamics, the tensor calculus inside materials. Again, he doesn't do the dispersion. As far as I remember, he doesn't do any Fourier transforms. So the issue of dispersion is still a problem there. And this is our problem in other words, we now understand conceptually what the UFO phenomenon is, but to now reverse engineer into operational technology, we don't, at least Jack Sarfatti doesn't understand. I don't know if Kip Thorne, I looked in Kip Thorne's book. Kip Thorne has a new book. You know, he's one of the best guys. He has a book on classical physics, a new big book he did with one of his students. And I looked there, there's nothing in Kip Thorne's latest classical, from 2 or 3 years ago. Spent the money, bought the book on Kindle, and he doesn't discuss this issue either. See, I can't find it anywhere. And if anybody, I asked this woman from at my club, this woman Catherine, she's from Oxford, astronomy professor, astrophysics, brilliant. And I asked her if she knew it, and she didn't either. She said, "Yeah, well, I guess she thought maybe there was one paper she heard of, but nobody's really done this. So this is unknown territory. How to correctly use general relativity concepts and even special relativity concepts inside highly dispersive anisotropic, what are called space-time metamaterials. It's an untrivial problem. Nobody really understands it yet. At least nobody I know. I don't understand it. I admit I don't understand it. And if somebody does understand it, please, get in touch, because until we solve that problem, we're not going to be able to make operational. We're not going to be able to reverse engineer what we see happening in the U.S. Navy, close encounters with this military technology. So maybe the Russians, maybe Putin's guys, I'm hoping if I do talk to these Russians in a month, that maybe I'll pick up some. Maybe they got it. Maybe the Chinese have it. Maybe the Iranians have it. Who the hell knows? But I don't have it. So if I don't, maybe the Israelis have it. I don't think they have it. I don't think anybody has it. Okay, so now let's get back to this. This is important. Here we depict flat space-time by keeping all the light cones oriented in the same direction as in the following figures. Now, this is Roger Penrose now. This is Roger Penrose. See, look, here's the field of dreams, the field of light cones. This is where there's no gravity. There's no curvature, there's no gravity. You can do fake gravity, what's called first order gravity, but there's no real gravity. When there's no curve, think of these light cones almost like spins. Think of them like spins and or dipoles or something. But these are 4-dimensional structures in space-time. When all the neighboring light cones are parallel to each other, there's no relative tilting. That's globally flat space-time, no gravitational field. Okay, and special relativity deals with that. It can deal with accelerating frames, but all the light cones are parallel to each other. It's like a ferromagnet. It's like the spin. It's like the magnetic moments in a ferromagnet in a single domain of ferromagnet. They're all lined up parallel to each other. So this is the picture. This is the Roger Penrose picture of flat space-time without any real gravity in it. Okay, it's called Minkowski space-time. Okay, and this is extremely important. Now look, let's go here. I guess I'll stop here. Okay, now I'm going to go back to what I was saying a little bit before, but now with using Roger Penrose's light cone picture, and in anticipation of the Alcubierre Warp Drive, I'm going to use the red cone. The top, these are the red are the future light cones, right? And the blue are the past light cones. Why am I using red for a future light cone? Because we're going to see in the Alcubierre Warp Drive case, the red light cone, that corresponds to a gravity redshift. That's for attractive gravity. And the blue half light cone is the anti-gravity blue shift. But right now, in this particular picture that I have here, there's zero gravity. But I'm just using that color code for later on. We'll need it. And remember I said, okay, so now we have Alice and Bob, right? Alice sees Bob in her past light cone with retarded light signals. Bob's future light cone is Alice's past light cone. Got that? In other words, if Bob is sending a message to Alice by light, or when I say light, I also mean any electromagnetic signal, what's called a far field signal. It can be a radio, microwaves, heat waves, X-rays, and there's no dispersion. This is all in vacuum now. If it's matter, we have a problem. We got a problem here, is that we're inside matter. But this is now all in vacuum or air, where air, well, even in air, there'll be a problem because air can be dispersive, and they have to make corrections. I guess in the GPS, this is actually practical. In all the various surveillance systems, they have to really correct for dispersion. If there's significant dispersion from the atmosphere, that has to be accounted for in their interpretations of the signals. But right now, we're just being simple, lazy, and we're just speaking about vacuum. So anytime you see anything, you're seeing in your blue half past light cone. And anytime you're transmitting anything, you're transmitting in your red here, future light cone. And in order for Alice and Bob to communicate by light, Alice's blue past light cone must intersect or mesh with Bob's future red light cone. And this is now all for globally flat, zero gravity field Minkowski spacetime. All right, now what happens when there's gravity? What happens when there's gravity is the next question. Okay, so now this is what happens when there's gravity in an idealized kind of black hole situation. Now, when there's gravity, like here we have matter, a star collapsing into a black hole, the curvature of space-time will then be depicted by the tilting of these light cones. Now, this is Roger Penrose's beautiful, intuitive way for anybody to get a grasp of general relativity, visually speaking, in 4 dimensions, but reduced to a 2-dimensional picture. The curvature of space-time will be depicted by the tilting of these light cones. The relative angle between 2 closely neighboring light cones will not be, they won't be parallel. It's kind of like non-Euclidean geometry. This reflects the fact that the causal structure of such spacetimes is different from that of flat spacetimes. So, for example, the spacetime around a massive body like a star will be depicted as follows. We have a black hole when the curvature of space-time becomes so severe that for some regions, there is no path out of that region that remains inside its own light cones. So that's, and that's pictured, now they don't actually draw it here very well. I should have gotten a different picture, but what happens is that the light cone here becomes like tangent. Well, any case, the cylinder there, that surface of cylinder is meant to be an event horizon. And that's the critical point at which the light cone becomes so severely tipped over, toward the interior of that cylinder that no light along the future light cone can escape it. Oh, I'll show you in another picture in a minute. I'll show you another picture. So it's a one-way membrane. So in this case, it's like God's cockroach hotel. It's a one-way membrane. You can get in, but once you're in, you can't get out unless you go faster than light, which you can't. You can't go faster than light materially because that would take an infinite amount of energy classically, unless somehow you can become a giant quantum mechanical object and quantum tunnel through the classical barrier. But even that's not possible in quantum mechanics, because it turns out the barrier is infinite, and you can only quantum tunnel through a finite barrier. You cannot quantum tunnel through an infinite barrier. And even if you put in quantum gravity so that the barrier is not quite infinitely large, but it's limited by the Planck length, it's still very big, still big. You can't tunnel through. That's not how to do it. Now, maybe there's already a wormhole. There might be a traversable wormhole you get out. Yeah, that's a possibility. And of course, if you have a warp drive, then of course you can get out, but we'll wait for that. All right, so here it's the relative. So the curvature, it's called the fourth rank Riemann-Christoffel curvature tensor, which in vacuum just becomes what's called a Ricci. We call it a Weyl conformal tensor. Inside matter, you get what's also called the Ricci tensor. So this is what curvature is the relative tilting of neighboring light cones. Okay, that's the curvature of space-time, and that's what gravity is. Okay, now this is a very important slide if you want to understand the so-called fast and light warp drives. And this is where a lot of people stumble, and they never understand this. Again, it's related. Okay, this is the mistaken view. The mistaken view is that, and this is what would violate relativity theory, classical relativity theory. The picture people have is that this is for conventional motion. This is like a UFO that's literally moving through space faster than light. Okay, that'd be like a tachyon. Now, that's not what warp drive is. This is not the picture of warp drive. You're going to see what the real picture of warp drive is. And thinking, unconsciously, this is like the old Newtonian. This is the like the rocket ship point of view. You have like a rocket moving through space, but somehow it broke the speed of light barrier, and it's moving like a tachyon. And this is not what I'm talking about. This is not warp drive. This is not what Alcubierre means by fast light warp drive. In fast light warp drive, you're still inside the local light cone. You'll see that in a second. Okay, so this is the mistaken view, and it's the view that a lot of people have. Okay, this is the old Newtonian conventional propulsion view. This cannot happen. This is the so-called tachyon. Tachyons don't, we don't need tachyons. Even Hal Puthoff had said, even I did back in Fred, well, back in the 60s, 70s, we didn't quite understand. In fact, we didn't understand this, and we were thinking like this. This is stupid. This doesn't work. This is wrong. And a lot of people in the military and engineers, they still think this way, and that's the wrong way to think. And that's a big stumbling block. Okay. Okay, now this is the correct way to think about it. This is the Penrose tilting a light cone. Here is an example of a fast and light warp drive. Okay, because what's happened now, okay, now look, Alice's light cone is now at right angles to Bob's light cone. Okay, but Alice is still moving inside her local light cone. So Alice is not actually, she's not moving in a way. Alice is still she's freely floating on a geodesic, on a time-like geodesic, no g-forces. But she is able to control, what Alice in her tic-tac warp drive time-traveling vehicle is able to do with small amounts of energy, she's able to control the tilting of her local light cone. And so she's able to tilt her local light cone relative to Bob's light cone. See, Bob is outside the warp bubble, and Bob is the ambient field. You can imagine that it's still kind of, you can imagine that, well, you can imagine it's Minkowski space out there, or even the space around the Earth. It doesn't really matter. But locally speak, so what has happened now? What has happened now is that Alice's future red light cone has become linked to Bob's future light cone. All right? So now when Bob sends a retarded signal along his red future light cone. Alice receives that signal as an advanced signal from her future, from her relative future. In other words, Bob sends out locally what to him is a retarded history signal. Alice sees that as a destiny signal coming in to her, all right? So, and that's because of that's the counterintuitive nature of curved space-time. You're able to control your local curvature relative to everything, the external world. All right, so this is fast light, FTL, fast light warp drive light cones are not parallel. There is no global past and future. The light cones are perpendicular to each other. Alice's world line is faster light relative to Bob's world line, and vice versa. It's reversible, right? Alice's future light cone meshes with Bob's future light cone. Therefore, Alice is able to see what is in front of her in her future from retarded signals from Bob. Okay. Alice controls the orientation of her flying saucer local light cone relative to the cosmological Hubble flow with small amounts of energy, using the effect that I first revealed at the DARPA NASA 100-year Starship Orlando October 11, 2011 meeting. So there we are. This is very important. And on your own time, you're gonna have to take this, and if you're a serious student of ufology and want to understand, and not not just swallow all the nonsense. It's not Lazar, element 115. It's not Mach effect thrusters and all this nonsense. That it's not the Pais patents. That's all junk. It's all junk pseudophysics. Okay, this is the right stuff. This is the real McCoy from Einstein and Roger Penrose and Sarfatti. Okay, and this is what you have to understand. It's going to take a while. It's not easy. Okay, now here is an illustration that I asked Julien Gaffrey in France to make for me. And this is an example of how to use a tic-tac warp drive to get safe from Earth to the moon in a couple of hours, even shorter, or better yet, to get from Earth to Mars in a couple of hours. And this is like for Elon Musk, Jeff Bezos, all these guys, all these billionaires who are still like little kids playing with giant firecrackers. And it's brilliant engineering, I admit, seeing that SpaceX thing come down and, reusable, that's all brilliant stuff, but it's all irrelevant now. It's all obsolete technology, okay? The people who controlling the Tic Tacs, they can get a Mars and the moon, and they're not going to take 6 months. What's going to happen? You're going to go. People could go stir crazy in a little tin can for 6 months. They're going to kill each other. They're going to die. They're going to. Something's going to hit the damn ship. It's a suicide mission. It's stupid. And who the hell wants to go to Mars anyway until you terraform it? I mean, I'd rather stay on Earth. But eventually we're going to have to get out. We're going to have to get out into Mars and stuff. But it'd be a lot easier if we could just get into a ship and be there in a kind of like going from Cortona to London, like that. That's what this gravitational technology can do. So all this stuff that's being invested by Elon Musk, it's brilliant stuff. It's great, but it's stupid. It's basically stupid, Elon. You better listen to what Sarfatti's trying to tell you. Okay. So this is just an example, an application of how to say go from the Earth to the moon in, I don't know, maybe 20 minutes. Who the hell knows? And of course, with a wormhole, you could even do it you just step through the door and you're there. And all that's now, all this metric, this is the new universe. This is, what the Pentagon has revealed, what the real disclosure is, I'm giving you the disclosure. Okay? The disclosure is the physics. Everything else is bullshit. They don't know what they're talking about. Okay, the main thing is the physics. Once you have the physics, you got it all, and now you have to convert that physics understanding into technology, and then that'll happen. I mean, it's obviously happened. except we haven't done it yet, but maybe we'll do it in the future, and maybe we're seeing our own technology coming back from the future, kind of like kicking us in the ass to get it done. So there it is. There's a particular thing. You can look at this, but I want to get to the two main points, two final slides for this session, which I'm avoiding doing algebra, doing the math. We could do that the third session. This is just the intuitive visual right brain. The left brain stuff will come next time if we get to that. There we go. Okay, now we're going back to the anti-missile defense shield. And on the left here is the black hole situation I was trying to mention before. If you follow those light cones, you'll see at the event horizon, that light cone right at the boundary there, the outer edge of the future half of the light cone is tangent to the event horizon surface. So that's a one-way membrane where particles moving at the speed of light, or even less than the speed of light, can get into the interior of the event horizon, but they cannot escape. And the white hole is a time reverse of that, just the opposite. Things can get out of the metamaterial, in this case, a metamaterial, if it's an artificial white hole horizon, I'll call it a quasi white hole horizon. Things can, inside they can shoot out, but they can't get in. But of course, they can't, the guys on the inside also cannot see anything because no signals from the outside can get in. They need little portholes or something. But that's an issue. And there are some technical things. This is highly speculative. The only reason I mention it is that there seems to be some anecdotal folkloric evidence that the Tic Tac, or whatever you want to call it, the flying saucers have this kind of technology, but maybe not. But the final slide for this session, this is the Holy Grail, time travel to the past, the time machine, H.G. Wells, time machine. Here it is. You want disclosure. This is disclosure. This is disclosure. The question is, are you smart enough to realize that this is disclosure? And are you going to listen to the Philistine, to the Pharisees who say it's not disclosure? So that's your choice. You're gonna be a doubting Thomas, or you're gonna see the Grail. Okay, here it is, guys. I'm pulling Excalibur out of the stone here, guys. But not everybody will be sharp enough, to see it. Let me wait a minute. Okay, so go ahead.
Okay. Right. Hi. Hello, Dr. Jack Sarfatti. I'm Charles Crawford III, PhD student in electrical engineering. I'm one of the naive engineers that are trying to think of a way to engineer this from your theory. So I'm interested in if there's any other anecdotal or besides flying saucers, objects or experiments that you've seen that might be related to your theory, like the Hutchison effect from John Hutchison. How he was able to levitate the cannonball. Is that related to what?
I know, John. I'm very aware of it. We had his girlfriend was part of the ISSO 20 years ago, Joe Firmage. It's I don't know what to make of it. Possibly, he has such strong electromagnetic fields that it could just be magnetism. Larry Lemke may know more about that. So it's. I don't know the answer, but we have plenty of evidence. We have evidence from the Navy, from the military. How much evidence do you need? We got more evidence from the military than they have for the existence of the Higgs boson and many of the effects from CERN. You can't reproduce those experiments. There's plenty of evidence. We have thousands of reports of UFOs. Throughout.
I don't think he's looking for evidence to suggest that such a phenomenon exists, but he's looking for something that can be done in a lab. Other ideas for what might be tried in a lab.
We have the closest we have in the lab is what Larry Lemke was talking about. I mean, I don't know. Look, the point is this. It's a condensed matter physics problem. We have to engineer these metamaterials. We see these things happening. There's only one way they can happen, and that's the way I've described. And if you believe in general relativity, unless you want to say there's some completely unknown physics, which to me is a stupid strategy for anybody to take. Because the one thing I learned from Hans Bethe and these guys at Cornell, you try to do as much physics you can with the least amount of mathematics. We have a perfectly good theory of Albert Einstein. It works, okay? And on that theory, there's a loophole in that theory, a conceptual loophole nobody's noticed, and it's not such a big deal. Everybody thinks the coupling constant is fixed at some weak value, but clearly what we're seeing is warp drive, and if the coupling constant is not fixed at a fixed value, then everything becomes obvious that this is, it's like Sherlock Holmes. But that doesn't, see, that's what the point I was trying to make. You can have a conceptual understanding without knowing how to go into the lab and do it right away. But you have to have the right idea to begin with. What is it you're looking for? This is what I learned from Hans Bethe as a theoretical physicist. This is what theoretical physics is all about. You got to get the right basic idea. You have to, look in the right part of the dark room. And then you figure, well, once you have the right concept, then, the engineering, all that stuff is going to follow. Do you see what I'm trying to say?
Yep. Yeah, I understand.
Yeah. Well, and, I should mention, let me see, Gianluca Perniciano is coming up next in about 10 minutes. But before that, let me go to Creon.
Yeah, he has the rest of the, because I won't be doing anything else, so there's plenty of time for him. Yeah. Okay.
Great. Thank you.
Okay. Thanks, Charlie. Creon, go for it, sir.
Okay, thanks. Hey, Jack. I'm rewinding back to your discussion in the recording of inertial mass, passive versus inertial mass, active versus rest mass, gravitational passive, gravitational active, rest mass, and inertial mass. And also there's something about Higgs and mass, which you didn't mention, and I'm not sure whether it matters.
Which? Higgs?
Mechanism and mass, which you didn't
that's
mention.
the inertial mass. That's rest mass. That's rest mass. Same as
Well, okay, but aren't rest mass and inertial mass different in this different meaning? Inertial mass is resistance to acceleration, whereas rest mass is mass energy relationship.
What's the difference? Okay, if you have a particle, if you have a fast cosmic ray, and you have this is an interesting question. If you have a fast cosmic ray, let's say a charge, suppose you have a proton, okay, a proton going very fast, and then you apply an electric field to it. I guess it's the relativistic mass, equal, right? It's not the rest mass. The resistance will be probably the relativistic mass. Is that what you mean?
Well, actually, my point is just to mention that I think there's the point that my minor point is that there is just like you can differentiate between active gravitational mass and passive gravitational mass, you can differentiate between rest mass and inertial mass. One is resistance to acceleration and one is E equals mc squared. Now, but the point is
wait, let's just be careful. We're not being, if I'm in the rest frame, I have a charged particle sitting there, okay? There's no electric field, okay? I switch on an electric field, the resistance is going to be the rest mass.
Yes. I'm not disagreeing.
So what's the difference?
Look, you're let's not go down that rabbit hole. What I'm trying to say is there are quite a number of different quote unquote masses that people talk about. And the weird thing about the world is that it seems that they're all the same. Like, even though they're defined differently, active gravitational mass, passive gravitational mass, rest mass, etc., they all turn out to be equal to each other. Now, what I'm asking is,
no, but that's not true. Wait, I don't think that's true. What I think is true is that the weak passive gravitational mass is equal to the inertial mass, and that's the Edvos experiment. Okay.
So would it be true to say that they're all equal in a flat space-time?
Not necessarily, no.
Not
because of no, wait. Okay, wait.
Oh no, but let me ask my question. Let me ask my question, Jack, which is the following: there are these different definitions of mass. In most physics, up until you and maybe a few others, it is curious that there's like this broader equivalence principle where they're all equal to each other numerically, if you, no matter how you measure them, and no matter which mass you look at, by which definition, they all turn out.
Wait. No, that's not true. You're being, no, you're not being precise. That's not true. Show me an experiment with an ordinary, ordinary sized laboratory particle where they measure directly the active mass of that particle.
Don't we get that when we calculate the small g factor for the Earth? That we've calculated.
No, what do you mean G factor for the Earth is, but that's the Earth. You talk about the
it's the active gravitational mass of the Earth. That's what makes.
But that's not a small. I'm talking about a particle. I'm talking about something you hold in your hand.
Fair enough. Okay, look, but my question is simply this: whether we argue about different experiments, these masses are usually assumed, or
they are assumed. Yes.
To be the same. What I'm asking is, in your variable S field theory, are you breaking that symmetry? Does that mean that certain definitions of the mass become decoupled, if you will, from other definitions and take different values?
Well, yeah, okay. I wish we had. I have to put the equation. Let's. Can we get an equation? I want to write down Einstein's. Let's put. Okay, you look. We have G mu nu, right, is equal to 8 pi big G over c to the 4, the S factor, okay, times the stress energy source tensor, right? Okay, so what it is, it's all I'm saying. I'm not changing the stress energy tensor. I'm just changing the coupling constant of the stress energy tensor to the, to the output gravity field.
Yeah.
So I'm
does
not
that mean
the mass at all? I'm not changing. Okay, but it's as if the active mass has changed, but it's really just the coupling that's changed.
All right, fair enough. Thank you.
Okay, it's like, okay, here's a good analogy. It's like in a dielectric, dielectric screening. It's the same as dielectric screening, with the bare charge, and it's like in a dielectric, you have a screened bare charge. So are you saying it's exactly like that? Are you saying that you've changed the charge? No, you just screen the charge. Because
all right, thanks for clarification.
Okay, I have a quick question, Jack.
Yeah.
I hope you can hear me better. I found my earbuds, and I think.
Oh yeah, that's better. You sound much better.
Yeah. Okay. Fine. So let's say you have your metamaterial there, happily being pumped into the state, and it's generating this field. Yeah. Have you considered or thought about whether or not that creates just a mechanical stress in the metamaterial itself? In other words,
I don't know. No, I haven't done that, but obviously, all I know is it's not a problem because we see these things flying around. There's
I'm not saying it negates your theory. I'm just saying I'm strictly trying to look at the engineering problem of.
No, I'm not the engineer. That's the job of the engineers.
Well, but if you had this metamaterial and it's generating this gravitational warp effect that propagates externally to it, does that not cause back reaction into the metamaterial itself? And the reason I'm asking this is because, again, getting back to the Roswell foil, one of the questions that often comes up is, okay, so you have this material, this memory foil that's, you can't shoot a bullet through it, it's super strong, and so forth and so on. What the hell caused it to break into a million pieces, and scatter all over the field? And the only thing
I have an answer for that. I have a possible answer for that.
Yeah.
The possible answer for that is something went wrong with the system, and the pump system. You have to energize the thing.
Yeah. Well, that's my point.
Yeah, and then it becomes like an
ordinary. I mean, it's like if you blow up a foil capacitor because you overcharge it, you'll get smithereens all over the lab, right? And it's because it's basically the material itself is building up internal stresses to the point where it fails essentially instantaneously, right?
Yeah.
And so what I'm wondering is, does that imply that in order that to create this field, you're basically energizing, you know, the material itself in a way that causes actual mechanical stress
Well, that's a question I have no idea, but let me
doesn't
say,
there have to be a
hey,
back reaction from the creation of
I don't know. I don't know, because that has to all be studied. If we had a serious effort, there'd be guys working on that problem. It's a good question. That's part of the nitty gritty of the engineering, but it's not the conceptual thing that I as a theoretical physicist can do. But let me say one important thing about this. Remember, this is time travel. We're talking about real time travel here. Okay.
Yeah.
So the Roswell, some of the stuff that apparently some of the early stuff in the 40s may be shot down even by, even when the Russians apparently shoot their bullets, they were able to disable some of these craft, allegedly. But there's also other stories where they try to shoot a missile and the missile bounces back. But that's simply but that is because we're seeing different stages of development of their technology, because they're coming from different time periods.
Oh yeah, I can easily believe that. Yeah.
Yeah. So we're seeing different generations of technology. Just like I say, it's just like we're seeing it's just like a World War I biplane versus an F-35. So and so maybe the ones that were shot down, then they went back to the drawing board, and the ones we're getting now, they're not going to be shot down so easily. So listen, everybody has to take it. Yeah. Now I know there are a couple of crazy guys. What was that guy? A bunch of these guys that said they were time travelers, and and they sound pretty nutty. But we're going to have to take that seriously in terms of like, is John Ramirez still here? Is John here? Ramirez? Is Ramirez here? Can anybody see?
I don't see him.
All right. But the point is, a lot of these, the CIA, the intelligence guys, they're going to have to sort of consider in their threat analysis, if it really is, it's got to be time travel. And that's a whole joker in the deck. This is a fly in the soup or fly in the ointment. That, these things, if you can control gravity, you can travel in time, any way you want to go.
Yeah.
But as I show with the light codes, this is all Roger Penrose's stuff. Once you have Roger Penrose's pictures, you could, that's the only way to think about these things. So there's no, the so-called chronology protection conjecture of Hawking. There's an easy way out of that, because it's not a closed time-like curve. There's a gap. It's like the toy. It's like when David Chester was talking about torsion. It's the gap. You don't actually you don't close the circuit. You don't close the curve. You just leave a little space there. There's no problem.
And that doesn't violate conservation of mass.
What? How? Why should?
Well, if you have the same object, if you have Alice existing in two.
No, it's not conservation, because they're different. No, you just look at the world line. There's no everything's locally conserved.
Okay, all right.
I mean, once you have time travel, I guess you could say, well, but locally everything. I mean, okay. This is a good question. Technically, the conservation of mass energy is like the forward divergence of the stress energy tends to vanishes, and that's a local relation, and that's always true everywhere along path. So globally, you cannot define. There's a big problem that globally it's very hard to define total energy in curved space time. You just can't do it. See, as Wheeler says, physics is simple when it's local. Locally, there's no violation. I mean, what is conservation of energy? Conservation of energy and momentum. That's all from Noether's theorem, symmetry. When there's translational invariance. Locally, on a small scale, you have your translational and time invariance, but globally you don't. So you can't even define these global quantities.
So would that suggest a CPT symmetry violation in this? Because if you make a minimal loop in time, you could loop energy back through it. and use the energy multiple times, sort of.
Well, I don't know, but okay, it's a good question, but that's the Hawking chronology protection. Yeah, if you try to make a closed timeline curve, you might get in trouble. Yeah, in fact,
Yeah.
okay, you know what's going to happen? Okay, yeah, Hawking might be right, but it doesn't negate what I'm talking about, because if I
Right.
were to be stupid enough to go back and try to close the curve, I may explode. You know, I may die trying to do that. But if I keep the gap, if I don't close the circuit, so to speak,
You mind the gap.
yeah, mind the gap. Don't cross the gap in this case.
Okay.
Mind the gap. So everything I'm talking about is actually consistent, even if Hawking is right about his closed time-like curve conjecture. It doesn't. This is the way. He forgot this loophole.
I'm
So
gonna have
both-
to sign off. I'm gonna have to sign off, Jack. So
Okay.
good talk to
All
you.
right. All right.
Okay.
there any-
So yeah, I think we got Creon, we got Charles. Do you want to go to Gianluca then?
Well, it's up to, if they have, okay, what time is it? Okay.
Yeah, it's 3 minutes after the hour.
Okay,
So
how long does Gianluca want to talk? How long is his talk? Find out, how long is his talk? How much time does he need? Because we started about 10 minutes late.
and let me see, he's here. Gianluca.
How much time does he?
Wonderful.
Oui, yes.
I think we should move on because we're, it's,
Well, I had one question. What exactly is the 3D geometry of this this warp field he's talking about here? Is this just a hyperbolic tangent symmetric around some sphere?
I don't know. Don't ask me. I don't know. I haven't read the paper. Why don't you read the paper and then communicate with him
Okay.
privately? No. The question is, how does he, in principle, what physical effect does he have in mind that would accomplish that metric form? I mean, that's the issue. I
It
have no
sounds like
doubt.
some layered metamaterial.
Well, I don't. He never. But he, you have to ask him that. Communicate. Privately. I mean, that's the issue. I'm not doubting. I'm sure his mathematics is correct. It's not a question of mathematics. It's a question of how to translate that mathematical model into a physical mechanism. But maybe so. I mean, it could be that what he's talking about. See, he's not talking about changing the coupling. He's using the standard coupling, but he has some other thing. But if there may be a way of combining both what he's saying and what I'm saying, who knows? And that would even be better. But we don't
If
know.
we're in open discussion, I would love it if you could elaborate on the space-like just like field that you were near field they were describing yesterday for
Well, that's okay. Well, that's simple. Look, just do the math. The math is this: if you have a like in meson theory, okay, if the meson has the UCAO, the old theory of nuclear physics, it's in any nuclear physics book. You have like the Helmholtz equation. You have a particle with a rest mass, okay, and if you just and if it's like the Coulomb potential. When you put in the rest mass, the only reason the Coulomb potential is 1 over r. The only reason the Coulomb potential is 1 over r is because the mass of the photon is 0. That gives you infinite range. But if you put in a positive rest mass particle, that Yukawa potential decays as e to the minus r over the Compton wavelength, okay? So that's an m. But if you have a tachyon, the m is imaginary. So instead of a decay, it's spatially oscillating. So it's infinite range.
right. Yeah, that makes sense.
Yeah. So the point is, that's pretty good. That's actually very good, because what Giovanni was saying is that since what was it? That what the momentum was small, the momentum was larger than the energy, right? The momentum was larger than the energy. And if you plug that into E squared is m squared plus p squared, that means m squared is negative. So that means imaginary. And yeah, you get infinite range. That's exactly what you should get. It's a totally consistent picture.
Well, then why aren't if it's possible to generate phenomena that do this, why aren't we getting pushed by these fields across the whole universe occasionally?
Well, maybe I don't know. Well, he did this in the lab. We don't know if it's happening naturally in astrophysics.
There must be some exponential. There must be some exponential envelope to the thing, I imagine.
Well, not necessarily. I don't know, but the point is, the basic effect is the basic thing is elementary. It's elementary physics.
Well, I know with the near field faster than light propagations that I'm aware of, usually they fall off.
That's different. No, that's different. That's not the same thing. That's not from an imaginary mass. That was near field. Who's the guy? I know what. There's a guy in Sweden who wrote, I forget his name. He wrote these interesting papers showing that in the near field, just with ordinary electromagnetism, that if you're in the near field, it's like an effective faster light, but then when you get into the far field, it slows down to light. That's a totally different math. That's a totally different. Don't confuse that with this.
Okay.
This is something else.
Got you.
He's saying that there seems to be an effective gravitational mass that becomes like imaginary, and that will give you a momentum that a P that's bigger than an E. Yeah. In other words, PC is bigger than E. Normally it's E squared is equal to M squared plus PC squared. So
that reminds me a lot of squeezed vacuum states. Because
I don't
they
see,
also have.
well, I don't see the connection. You may be right. You just have to work out the math. Does a squeezed vacuum give you an imaginary mass somehow? How do you do that?
Well, it's when you square the wave function to get the probability, you don't just get it doesn't sum to like a real number. It has an imaginary component when you square the wave.
No, yeah,
function.
no, but all that's, no,
But
I
the Wigner
I don't think
function
that'll
is
work. I think you
strictly
could,
positive.
I think that's apples and oranges, because all you're doing there in a Glauber state, it's quadrants, it's just about the electric field that you can measure like one quadrant, what do they call it? You can measure one segment.
Quadrature, yeah.
But then you get more uncertainty in the other one. So that has nothing to do with mass. I don't think that. And besides, he's talking about gravity now. He's not talking about electric. Well, you could have a Glauber state of gravitons, but I don't see the connection there. I think that, I could be wrong, you could be right, but I don't see, I think you're mixing apples and oranges there.
I may be.
Yeah. But the thing is this, what he did say made a lot of sense. What he did say, he has a space-like, what he has, in superconductors, the photon inside the superconductor gets a rest mass. That's called the Meissner effect. Okay.
Yeah.
So it also is looking because through Einstein's equation, the electromagnetic field gets converted into a gravitational field. It's that the graviton in there gets a rest mass too, but somehow he's getting an imaginary rest mass for the graviton, and that will definitely give the effect he's talking about. That'll give an infinite ray. It doesn't decay. In other words, it's a spatial. Oh, this would be interesting. All he has to do, it's like a standing wave. It's gonna be like a standing wave, probably, and there'll be regions of maximum impulse and regions of zero impulse. It's like a standing.
Yeah, that would be interesting.
wave.
That'll test that.
In other words, if you move the target in space, at different if you do a series of experiments at different distances and see if the effect goes away and comes back, then you know for sure that.
Oh, that's interesting. Maybe that vaguely reminds me of neutrino oscillations and their own.
Yeah, it's like that. Exactly. Yeah, it's sort of like. Yeah. But okay, let me make the important point. Everything that Giovanni was talking about with superconductors at low temperature, we can do at room temperature with the Froelich effect. We make now there's all this stuff about which is kind of irrelevant too. There are all these guys who were trying to check out Froelich's biological application of the phonons and with electric dipoles in biological membranes. And there's some papers that it doesn't work there. Maybe it doesn't, but there are also papers that it does work there. So there are conflicting experimental papers on that particular issue. But that's not what I'm talking about. I'm talking about much more general. I'm talking about the Froelich's effect is not limited to phonons in with these electric dipoles, like the microtubule. It's not limited to that. That's one application of it. All Froelich is talking about, he's talking about the laser equations. If you go back to the original guys who did the laser, their rate equations, he's just talking about the laser equations, but not for photons, in general for quasi-particles inside a material. You get the same thing happens. Okay. So
right. So you're trying to create some sort of condensate in the material, but in Modenesi's thing, wasn't he talking about the most effective way of getting repeatable experimental result was bringing something through the superconducting transition and then back out, or doing so as quickly as you can.
Okay, that may be. So what? So you have the same thing.
So is it then we create this condensate and then destroy it alternatingly, or like?
Yeah, well, you could do that. Whatever you could do, whatever Modenesi does with his superconductors, you can do at room temperature with Froelich condensates. The mathematics is the same. It's all
well, why would it? I mean, with superconductors, because of the conductivity, we see. Well, the superconductors, part of the reason why it's having this rest mass of the Meissner effect and all this in the material is because of the electrical conductivity specifically. So you need to have
No, that's not right. No. The reason you get the Meissner effect is because you have macroscopic, you have an order parameter, condensate order parameter. That's what does it.
Got you. Okay. Yeah.
Okay. And it's exactly the same mathematics.
Okay. So you to get this rest mass interaction, you need this order parameter. And
Yeah, you need the auto parameter. That does it. That sort of gives you when you look at the wave, when you look at the Landau-Ginzburg equation, you take the static limit. It's a Helmholtz equation. So, and with the Helmholtz equation, that's your, there's an effective rest mass that depends on the square of the order parameter, the squared modulus of the order parameter. It's exactly the Higgs. It's the Higgs mechanism. It's the same.
okay,
Same thing. It's the same thing. The same basic idea of the Higgs mechanism, except it's a condensed matter version of the Higgs mechanism. But what I'm trying to say here is that Modenese is talking about equilibrium, thermodynamic equilibrium, and for superconductors, you have to go to low temperature. The Freudic effect is not an equilibrium. It's a non-equilibrium. It's like a laser non-equilibrium system, which is being pumped by an external energy source. That external energy source, as you increase the power, the pump power input is like an inverse temperature, mathematically. Right. So as the pump power input goes up, the effective temperature of the system goes down. So that's the point. And then it reaches like the critical temperature, and that's the lasing transition. So same thing. Everything that Modenese is doing, we can throw away his cryogenics. We don't need superconductor. We don't need any of that. All we have to do is find a metamaterial, pump the metamaterial, and get some kind of further condensate of some emergent quasi-particle. See, there's the other thing. They know that in these materials now, when you go into these non-equilibrium states, a whole new physics emerges. You have quasi-particles that are in the thermodynamic equilibrium state. They have a whole new zoo of possible excitations that occur above a critical, power input to the metamaterial, or any even ordinary crystals. It doesn't have to be a metamaterial, but a metamaterial is just an artificial crystal we can engineer, the way we want it. But this happens even in natural materials.
So what would be your best candidate quasi-particles to work with? I
don't know. Well, I'm not a condensed matter physicist. That's why we need a real thing here. You have all these frauds in the now this gets right back to what John Ramirez was saying and what John Warner was saying. You have all these guys. I just saw Aerospace Corporation gets $1 billion. They just got $1 billion about a year or two ago to do black projects like what we're talking about. But who's their physicist? They get Eric Davis, who doesn't know shit from Shinola. I'm sorry, pardon my English. They get all these second-rate guys who don't know anything. I mean, so they're not going to do anything. They're wasting all this money. So, the point is that if you get the right team together with the right funding, and we're talking about, $1 billion effort. You have to get the right, people together. I can't solve all these problems. It's like it requires a Manhattan Project. So until that happens, the Russians invited me to Moscow. They want to get, but I don't think they have the resources to do what the United States can do. But who knows if we're going bankrupt too. So who knows what's going to happen? Yeah, everything's up for grabs.
What, Jack, if I could jump in very quickly. So I'm going to do the write-up for this later today. So today's presentation that you did was Advances in UFO Metric Engineering Physics Part 2, right?
Yeah, there's going to be a Part 3, which I actually have done already. Then it'll be a Part 4, but we'll do that next week.
Perfect. Yeah, and I'll be there for you, sir.
Yeah. So it's 9 o'clock. Do we want to quit now? Or what? Does anybody have any pressing issues that they want to bring up before we quit?
Well, I guess my only thought is with the discussion with yourself and Michael, he is very much into material science. And so he might be, he's the #1 candidate that I know of for your metamaterials.
Yeah, well,
with the analogy to the Higgs mechanism, I should be able to figure something out.
Yeah, well, start working on it. And what we need is a team of condensed matter guys, who will start thinking along these lines. I mean,
well, I think John Ramirez, I'm not sure if John is still here. He'd said that there might be a September announcement, from Aero. One of the things that intrigued me.
The problem, we have a political problem, because the problem is right now, unfortunately, Christopher Mellon somehow, I said something about Donald Trump, so it got him pissed off at me. Christopher Mellon has the access, and his team is Hal Puthoff and Eric Davis. And I like Hal, but there is they are Eric Davis viciously basically defamed me at the Huntsville meeting because I had a couple of people, my spies were there, and they told me. And and that's a big issue, you see, because Chris Mellon has the ear of Avi Loeb and all. Well, they're sucking all the oxygen out of this. They're globbing on to the Senate Intelligence Committee. You know, Mellon is a Mellon. He's probably putting his own money into it. So I have John Warner, I have John Ramirez, and maybe a few other guys, Rick Doty, maybe. You know, so it's a question who's going to win here. But in the meantime, the wild card is that Vladimir Putin, I was told, is interested in Jack Sarfatti's physics. I was told this 5 years ago. I was told this by Russians when Obama was the president. It had nothing to do with Trump, okay? So the Russians invited me to Moscow. So I don't know. I mean, what's wrong with this picture? So
I mean, you got a whole bunch of wealthy, got a whole bunch of wealthy plutocrats like raiding the shop store while there's fires in the streets, and it's not a good situation. It's a kind of all a collapse, like Tim was saying, but we got to make the best of it. And
whatever's going to happen is going to happen. Which is hey, but it's all coming back from the future anyway. So whatever, we just got to go along with the flow and see what happens. I mean, we know these things are out there; they're there. So the only issue is it going to be American technology, or is it going to be Chinese technology? Or is it going to be Russian technology? And by the way, you know who also I was contacted by Iranian physicists in Tehran. I haven't been directly contacted by the Israelis, but Frank Milburn, writes for the Mossad, for the Israelis. So it's very strange that there's a strange silence. So
so Jack, what's the issue with Hal Puthoff's polarizable vacuum model again?
It's bullshit. It's total nonsense.
Well, it leads to experimentally testable things.
Yeah, but do you see any experiments that work? If you actually look on Wikipedia, there's plenty of things of physicists, mainstream physicists who've looked at it, said it doesn't work. It's general relativity. It's the same as Woodward's thing. It's not general relativity. It's not consistent with mainstream physics. Okay, and the point is, all that Hal did in his metric engineering papers, he doesn't ask the correct questions. He doesn't actually show the mechanism for how to actually get a warp drive. He doesn't show any of that. All Hal does is to say, if there was some kind of a warp drive, what does the guy far away outside looking in, what does he see? What does it look like to him? That's the question he asks, but that's an interesting question, but it doesn't explain how you get the warp drive. And not only that, he doesn't even answer that question correctly because he's using a Mickey Mouse, he's using a trunk, he's using a bad model. He could have just done it with general relativity. He doesn't have to go to some little scale or approximation. He could just do, everything is doable within the standard general relativity framework. And that's what he should have done. But he's an engineer, he's not a physicist.
Right. So the engineering approach, at least, viewing the vacuum as a variable index medium and mapping that to curvature.
Not good enough. That's not good enough. That's not good.
Because if it's variable index, then you can.
Okay, but there are two indices. Wait a minute. There's the gravitational index of refraction, which is simply an analogy. Okay. Well, and it's correct. What he's saying is the same what I'm saying. The coordinate speed of light in vacuum now, just in vacuum, the coordinate speed of light depends upon the curvature field. And that is correct. I agree with that. When Hal says that, I agree with that. But that's the coordinate speed of light. Okay. But, and that's correct. But there's also, what I'm talking about is the ordinary refractive index of electricity and magnetism in the material. That the electricity and magnetism, so to speak, I'm oversimplifying, the index of refraction of ordinary electromagnetism of real charges in real materials, that variation in the electromagnetic index of refraction will affect the induced gravitational field. So there will be a mapping from the electromagnetic index of refraction to the gravitational index of refraction. That's true, because the gravitational index is just showing how the light rays, bend. It's gravitational lensing is all he's talking about. Okay.
Right.
So there is a connection between the two of them, but Hal never says that. Hal never there's nothing in his math that shows given a block of material, I don't care what it is. Hal has to show, given a block of material with an electromagnetic field in that material, and there's like an index of refraction, that material, how does that translate into the gravitational index that he's talking about? He doesn't.
Well, he kind of does. He kind of does, because if you look at like where you're near nuclei, you have the fine structure constant. You can interpret that as a refractive index.
No. That doesn't work. Yeah, it's just no.
Well, the Feynman diagram. Well, anyway, that's a
no.
That's the high energy limit of gravity. That's the nonlinear.
It's not. That's not going to work. If you think, write down something on paper. Write it down and see if you get something to work there. It's easy to.
I'll play around with it.
No, and besides, what you just said doesn't sound like anything Hal was doing. That's not what he does have a. He does try to do a Lagrangian. He does make an attempt. He has a single like electron in an electromagnetic field with a vector potential, and he tries to get a gravitational field from that. But it's just a very Mickey Mouse model. It doesn't lead anywhere. He doesn't show any. And then the other thing is this, that
it leads Schwarzschild.
Okay, now here, let me complete this thought. Hal does have access to classified material, and so does Eric Davis. Okay, they have access to classified material, and so does Louis Elizondo. Here's the intelligence. And let's look at the defense situation here. Okay, they have access to classified material, and so does Mellon. Okay, they have leaked out important information that I am very interested in. They leaked out metamaterials, right? That happened in when did you first hear Elizondo talk about metamaterials and UFOs? About a year or two ago, maybe 3 years ago, around COVID, around 20, not before 2017, right? Not before 2017. Nobody heard of Louis Elizondo. He only appeared about 2019, 2020. I already was talking about metamaterials and UFOs at the DARPA conference, in Orlando, and it's and there's Sharon Weinberger wrote an article about my talk there, so it's all on record. Jack Sarfatti.
Maybe not Hal put off specific model, but in general, you can imagine a field with vacuum fluctuations that differ from place to place. And one region has more, one region has less. That would cause the refractive index due to the interaction of the light with the virtual particle.
But Hal didn't do it. I actually have a model like that.
But because they're virtual, they don't necessarily have a reference frame that's their own.
No.
You can have something like refraction, but without a reference frame.
No. Now you're going off into la la land. No, the point is this. It's very precise. From Einstein's field equation, you can make a stress energy tensor for the Casimir effect. Okay, it's easy to do. And it turns out with my S field, when you do that, you do get something that looks kind of interesting. I haven't had a chance to work it all out, but it's all very, it's all just using standard physics, just using Einstein's equation, and there's a stress energy tensor for the Casimir effect. You stick it in, you see what happens, and there may be an effect there. I'm not saying there isn't, but Hal didn't do that. He didn't do anything like that. Okay.
Well.
But let me get because you're interrupting me, and I had a coherent story I was trying to communicate to people here.
Go ahead.
So just keep quiet for a minute. I forgot what I was going to say. All right. No, the point is,
Hal?
yes, I remember now. The point what I was trying to say is Hal Puthoff and Eric Davis have access to classified material. So does Louis Elizondo, and they started bringing up. Years after I mentioned metamaterials in this context, at the NASA DARPA conference, which by the way, the Russians were there listening to, they started talking about metamaterials. Hal talks about in his lectures, metamaterials, but he never connects how these metamaterials create the gravitational manipulation. He doesn't show it. Why doesn't he show up? Because he has because they don't know how.
Or it's classified.
No, it's not because it's easy to show how. I actually did it in public in 2011 there was DARPA, NASA. Larry Lemke was there. Eric Davis was there listening, but bad-mouthing me at the time because they didn't want to talk about UFOs. I mean, it's the whole thing there. Sharon Weinberger writes about what happened back then. Okay, so I had that idea. It's in public. It's out there in the internet already as of 2011. My paper's circulating around all over the place. 7 years later, they come out saying it, but they don't give a connection. They don't give the equations. Well, I already gave the equations. It's not hard. It's not that it's classified. How can it be classified when it's simple? When any graduate student at Caltech or MIT can figure this out.
Fair point.
When they classified, it's stupid. It's stupid. Okay, but what they're doing, and as John Ramirez says, they're preventing, say me, from getting access to that information. And in doing that, they are damaging the national security of the United States. But of course, right now, the president of the United States is damaging the national security. So I guess who cares? But in the meantime, the Russians, they have a crash source also. They have it, and they have smart guys. And the Russians consider Jack Sarfatti to be a serious person. I can prove that. Besides that they invited me to Moscow next month. But there's a whole history of me and the Russians, okay? So while Christopher Mellon is preventing Jack Sarfatti from access to this material, the Russians are taking my stuff and God knows what they're doing with it. Because they have the same. Do you see what I'm saying? You understand what I'm trying to say here?
Yeah. Yeah, I see it.
This is a serious situation. This is a bad situation. And the people, now I think John Ramirez, who's the ex-CIA, and he has his connections. John Ramirez is telling his people what I just told you. So we'll see what happens. There's all this factional struggle within the military-industrial complex. What are they going to do about it? They're going to let the Russians win? That's what they're doing right now.
I don't know. Maybe they're too infiltrated to do anything about it at this point.
But well, that's another point. That's another point. Yeah, because now we're getting into politics. You may not want to put this on the internet. I think John. Okay, this may be now off the record. Okay, are we recording?
Yeah, we're recording now.
Okay, I'm using first, the idea is you make it as simple as possible without making it simpler than is possible, right? Right now, I'm just using standard plain vanilla curvature 1916 Einstein's theory, seeing how far I can get with that. And I think I can get very far. So all I have are spin 1 photons that get converted into spin 2 gravitons by way of the Einstein equation. You can make it Feynman diagrams if you want, like Feynman did. And I don't have any of these exotic, in other words, the connection is just the Levi-Civita connection. Now, it may very well be because of quantum spins. I think David Chester has a good point. I do suspect that when we actually start doing this thing in detail with enough competent people working on it, I think all this mathematics that David Chester is showing with the vector the gravity photon, it's like a spin 1 gravity field plus a spin 0 gravity field, the scalar vector tensor gravity, which may come from these other connections, from torsion. The torsion connects the spin, and even this non-metricity that he's getting. I think all those things may actually be important inside the material when it's pumped in the further condensate state. I would not be surprised if that happens.
Yeah, I would be surprised if it wasn't the case.
I would be surprised if it wasn't. Yeah, yes, I agree. Yeah, that's my intuition also.
Yeah. Okay, that makes a lot more sense. I understand that a lot better now. But there's still some, like the graviphoton really sounds very similar to the generalized Glauber state with squeezed vacuum, though. Like it's a photon-like object, and you have variability in the background noise. And if that noise corresponds to a refractive index, you've got a wave in refractive index in space.
They all these, any emergent quasi-particle, collective mode, say, that happens, that carries a charge is going to affect the refractive index. By the way, but it's not just refractive index. It's what it really is. It's susceptibility response function, which in a special case becomes a refractive index. The refractive index only applies to far field, transverse polarized radiation going through the material. Okay.
Mhm.
It's the near field is off mass shell. The near field. So what you generally have is called a susceptibility response function, which is in wave, in frequency wave vector space. It's all over wave vector space, and the refractive index only refers to a surface, a constraint, like omega squared is equal to k squared, c squared, plus maybe some other stuff. Okay, that's called the mass shell, or the dispersion relation, so to speak. The propagating stuff, the far field propagating stuff, only corresponds to a subspace of Fourier transform space. Okay, but the effects the warp drive is off mass shell. We're not talking about radiation.
Right. I mean, you don't want to even because you'd waste energy that way.
That's right. Except when Monesi was talking about the IgG, the impulse. That's the beam weapon.
Well,
When
right. If you
can, you want to make a gravity.
If you get a different ratio of momentum to energy, then that's
Yeah,
beneficial.
right. So both okay, so let's put this way. Here's what I'm saying. The near field, the off mass shell thing, is for the propulsion, for the warp drive itself. That's near field. It's not. But when you want to shoot down a missile, that's the other. That's the fact. That's what Monesi says he saw. But he saw that beam, affect the target. So
I really wish he'd gone into the math more.
Yeah, well, apparently.
Well, maybe next.
Okay. So, by the way, where is Tim? Are you there? Are you here, Tim? I think Tim probably went to the bathroom. But the thing is, okay. But when Monesi actually had a talk ready for that, but he ran out of time. If I would have known, I wish he would have done the theory and not done the experiment, because we don't. Who cares about the experiment? Because they didn't work.
Oh no, I'm here. I can hear you. My headphones are on even in the bathroom. So
okay, all right, okay. So the point is this: you need to post. Ask Monesi to give you his theory presentation and post. Okay, and well, that's all right. I'm getting hoarse already from talking too much.
Thanks, Jack.
All right.
Yeah.
Anybody else want to say anything? Does anybody have anything they want to add? Go ahead. He wants to talk.
I think he was just waving goodbye for the day.
Okay,
But
anybody else?
Thanks,
Okay.
Gianluca.
yes, thank you.
Yeah.
Okay,
So listen,
thanks everyone.
If Luca could give you a PowerPoint, ask Luca to make you a PowerPoint of his paper, just the slides, okay? And he could just show the slides, because I think, the paper's important. The paper may be important. We don't want,
I'll do some editing. I'll do some editing and see what I can get.
or see if you could just, see if he could send you the paper, and you could just, screen capture different parts of paper and just put into a PowerPoint.
And I think what you and Michael were discussing was incredibly valuable. I don't think I've ever heard any of that anymore.
I forgot what we said.
Well, that's why we record it. I think that the things you went through, it seems like you're laying more of a groundwork for maybe how to potentially create these metamaterials.
Yeah. By the way, you know what? I saw some stuff that John Ramirez wrote on the chat. Here's what I think. I think everything depends upon what John Ramirez is going to do with his intelligence connection. I don't know how much influence he's got, but it's up to John Ramirez to get the message through, because he is CIA. And by the way, I know people from my club who know John from the CIA. There's one guy, so I know John Ramirez was a heavy hitter. He's a serious guy in the CIA. So it's up to John to penetrate through against the Chris Mellon faction. All right. Okay, so we say goodbye?
Okay. Well, thank you, everybody. And so we will be posting some more next week. Wonderful conference.
Bye-bye, everybody.
All right.
Okay, have a good weekend.
Yeah.
Meantime, okay, yes. Listen,
Are you coming back tomorrow?
You guys talk to Gianluca and try to get, maybe he could explain it to you and you can talk. You know, he could do a PowerPoint. Yeah, we're off.
Okay. Yeah, let me close things down for today. Thank you again, everyone. This has been an
Are we back
absolutely
tomorrow? Is it tomorrow also? That's it.
no. I think today was it, and then Jack has more that we will put up next week. We'll add that.
Okay. Okay. Great job, Tim. You
Good,
did a
thank-
great job.
Thank you.
Yeah,
Thank you.
thanks, Tim.
Have a wonderful weekend, guys.
And everybody, Rob, I'll be talking with all you guys on the email.
Yeah. The conference never really ends with the
Conference
email.
room. It's the Sarfatti virtual roundtable.
Okay.
Yes.
I'll close things down for today. Have a great weekend, everybody.
Okay, you too.